The reason that we're doing the calculus of variations is to lead up to Lagrange's equations, which are yet another way of writing Newton's second law and solving, in particular, problems that are constrained, such as a ball rolling down along some kind of a surface. Lots of constrained problems can be easily solved using Lagrange's equations. That's the end goal. But to get to that end goal, we need the calculus of variations. The calculus of variations that we introduced in the last concept states that if you want to extremize an integral, then you have to, the functional, that's the integrand of that integral, has to satisfy the Euler-Lagrange equation. So the end goal is to get to Lagrange's equations, which are not the same as the Euler-Lagrange equation, but they're closely related. They involve the time instead of the position. But in the meantime, the calculus of variations, as stated, offers some pretty interesting things, interesting problems. And one of them is this one. How do you find the shortest distance between 2 points? Well, you say it's along a straight line between those 2 points. And I say, prove it. And you say, I don't know how. And I say, you probably never have proved it. In high school geometry, it was probably some kind of a postulate for you. Today we're going to prove it using the calculus of variations. So we're going to try and show that the shortest distance between 2 points is along a straight line. Let's say our 2 points are point 1 and point 2. And we have those in a plane, y is a function of x, Cartesian coordinates. And I have some function y of x that describes this path that I'm going to take from point 1 to point 2. And I'm going to ask what y of x must look like or be in order to minimize the distance between those 2 points. And you would say, well, Dr. Edwards, the y of x equals mx plus b. And I would say, very good. You're right. Prove it. And so now we're going to prove it. We're going to look at an arbitrary path y of x and show that that path must be a straight line. So how to do it? At one particular point x, this would be point y. Y is a function of x at this point. And I'm going to consider that little distance, element of distance ds, between x and x plus dx. This point here to this point here. How far do I have to go to get from x to x plus dx? Well, I've got some horizontal distance and I've got some vertical distance, dy, and the distance traveled between those 2 points here and here must be given by the Pythagorean theorem. I think you'd all agree with that. We use the Pythagorean theorem to find that hypotenuse distance. Let me rewrite that by factoring out a dx squared underneath the square root. Factor out that dx squared, and then, well, let me do it. Okay, I've just factored out the dx squared. From this term, I just get 1. And from this term, I get a dy squared over dx squared. Well, y is a function of x. So this is just one plus dy dx quantity squared. And then I have a dx squared, square rooted. I can take that out. And it just becomes dx. And now, dy dx, well, that's just y prime. So we now have and that's a little element of length that I need to get from here to here. Well, how do I find the total distance between point 1 and point 2 that I'm trying to minimize? Well, wouldn't I just add up all those little ds's from point 1 all the way up to point 2 in order to get the total distance? And that's correct. I'm going to call that capital S is an integral of ds. So I'm just going to add up all those little contributions to get the total distance between point 1 and point 2. Well, that is just square root of 1 plus y prime squared dx from x1 to x2. So I'm going to be a little clear here. There's my value of x at point 1, and here's my value of x at point 2, and I'm going to integrate from 1 to 2. That's the integral that I want to do. So this is the total distance. From 1 to 2. Is that capital S? Well, I want to show that I can minimize that distance by going along a straight line. This is in fact a calculus of variations problem, and let me restate it for you from concept 6.1. If you have an integral of f of y, y prime, and x dx from point 1 to 2, you can extremize this integral by saying that this function f must satisfy the Euler-Lagrange equation. That's the Euler-Lagrange equation. If you can satisfy this equation, then you will have extremized this integral. That's concept 6.1. So now back to this problem. Does this problem look like this? Are we trying to extremize this integral? And the answer is yes, we're trying to extremize it. In particular, we're trying to minimize it. We're looking for a particular extremum. The Euler-Lagrange, or the Lagrange formalism, can't tell you whether the integral is going to be a minimum or a maximum. It just can tell you it's going to be one or the other. So yeah, we definitely do want to extremize this integral. And to extremize this integral, we have to satisfy the Euler-Lagrange equation. And all we have left to do is to identify what f is in this particular problem. Well, if I compare this equation 1 to this equation 2, they both have the same form, and whatever is the integrand here must be f. So this guy f must be this guy, right, this square root right here. So comparing 1 and 2, implies that f is the square root of 1 plus y prime squared. Okay, so let me ask you, what does this f depend on? Does it depend on y, the function y? no, there's no y in here. There's a y prime, so it does depend on y prime in this case. Is there any dependence in this function on x? Well, there is a dependence on x through y prime, which depends on x, but there's no, and that's assuming you have an arbitrary y prime, there's no explicit x dependence. So this really only depends on y prime, and not on y, and not on x. So we're going to apply equation 3 now, the Euler-Lagrange equation, and see if we can solve the calculus of variations problem. Well, I need df by dy. Well, what do we mean by a partial derivative? For a partial derivative, you have to explicitly state which variables there are and which you have to hold constant. So f, the variables, the independent variables of f are y, y prime, and x. So when you take a derivative of f with respect to y, you're going to hold y prime and x constant. So I want to take the derivative of this function f with respect to y while holding y prime constant. What does that give me? Well, y prime is a constant. You take a derivative with respect to y, and there's no y there, and so the derivative is 0. So that makes our lives amazing. What about df by dy prime? We'll need that here too. We need df by dy, we need df by dy prime. What's df by dy prime? Well, here's f, and it does depend on y prime. I don't have any y's or x's in there to hold constant because there aren't any in there. So we just have to worry about taking the derivative with respect to y prime. Well, it's a square root, so the derivative of the square root is 1/2 times whatever's inside raised to the minus 1/2 times the derivative of the inside. So the derivative of the inside of the square root, the 1 doesn't have a derivative, but the derivative here will have a 2y prime. And remember, I'm taking a derivative with respect to y prime. So that just gives me a 2y prime. All right, and now we can substitute these into equation 3. df by dy is 0, we figured that out, minus d by dx of df by dy prime. Well, here's df by dy prime, and I got a 1/2 that kills this 2, and a y prime out in front, and so we just have y prime times the square root. Well, it's 1 over the square root. All right, and that d by dx, this is supposed to equal 0. Well, can you integrate that? The answer is yes, you can. Let me write it in a slightly more provocative form. Well, this 0 doesn't hold any weight. Let me multiply both sides by a minus sign, and we just get d by dx of y prime over the square root of 1 plus y prime squared. And that's supposed to equal 0. Can you integrate that equation? Yes, you can. Suppose I multiply both sides by dx and then integrate. Multiply the dx times 0, that's just 0. And then we have dy prime So all I've done is multiply both sides by dx, and then I just have the differential of this guy equals 0. Well, the integral of d anything is anything. And so, and the anything in this case is the guy in parentheses. Therefore, y prime over the square root of 1 plus y prime squared is equal to 0. And you say, no, Dr. Edwards, it's equal to a constant of integration. All right. That looks pretty bad. But it's not that bad. What I'm going to do next, in order to try and figure out what y prime is to multiply both sides by the square root of 1 plus y prime squared, and then square both sides of the equation. So this guy will go over here, and then I'm going to square both sides. That'll leave me y prime squared on the left side. On the right side, I'll have c times the square root of 1 plus y prime squared, which gets rid of the square root. Takes care of that. And now we can solve for y prime quantity squared. Y prime quantity squared here's a y prime squared, and here's a y prime squared, and it's multiplied by c. But if I subtract c y prime squared from both sides of this equation, then the cy prime squared will be eliminated from the right side and appear on the left side. And on the left side, it'd just be c times y prime squared with a minus sign, and so that just ends up being this term here. And that's all equal to c. And then finally, y prime quantity squared equals c over 1 minus c. And y prime, take the square root of both sides, it'll be plus or minus square root of c over 1 minus c. Now, I might ask what that tells us about the world. And you might answer, well, hang on here just a second. C is a constant. So 1 minus c is a constant, and c over 1 minus c is a constant. Let's call it m. That means that dy dx equals m. And I believe that you can integrate that equation with m being a constant. Multiply both sides by dx. Integrate. The left side becomes y. The right side, let's see, we're running out of space. Let me actually use this space right here to finish this off. dy equals m dx. Integrate. Integral of dy is y. Integral of m is a constant. Take that out of the integral. Integral of dx is x. Plus another constant of integration. Let me just arbitrarily call it b. And I would therefore ask you what kind of a function this is. And you say, it's a straight line. And I say, good for you. A straight line. And we can certainly make sure that that function y of x passes through point 1 and point 2 by choosing the values of m and b correctly. You have two pieces of information. It has to pass through point 1 and it has to pass through point 2, and you have two constants to make sure that that happens. So we have just proven that the distance between the shortest distance between 2 points is along a straight line that runs between those 2 points. And it illustrates how powerful the calculus of variations is. There are many other applications for the calculus of variations problem. One of them is a brachistochrone problem. It's discussed in your book, and I'll give you some homework to think about on that as well. But basically we had an integral. It's right here. And we wanted to extremize it. We wanted to find the function y of x that minimized this integral. We're trying to find a function. And this guy f here is a functional, a function of a function, and we know what that function is for this particular problem. For Euler-Lagrange, or for calculus of variations problems, almost always this functional is going to be known. And then you just simply apply the Euler-Lagrange equation to solve it.